We are supposed to be live now.
Okay, good. So yeah, so I'm going to play this tune that I wrote 45 years ago as part of my application for the Mechanical Universe series. And because it didn't get used for that, I'm going to use it for this series. So this is called the Mechanical Universe. Okay, welcome everybody to the Newtonian Mechanics series, the first episode of the Newtonian Mechanics series. We're going to be talking about static equilibrium today, and this will be an occasional course that I'll be doing in the Bitophysics series to make a sequence a sequence that explores basically just Newtonian mechanics. It kind of takes the work that Newton did. We probably won't even talk really about gravitation in this course, but just literally Newton's laws of motion, and approaches them a little bit differently than what is usually done these days in introductory physics, with the primary thing being the placement of acceleration in the list of topics. If you open the slides at the top of the room there, you'll see, as usual, the title. This is Bitophysics number 80. I'm John Mallinckrodt, your host for Bitophysics, a retired physics professor looking for work in retirement, and I guess this is what I found. And there are links on that page to all previous Bites of Physics and a bunch of other things that are in my public documents. If you go to slide 2, a little bit about what I intend to do here. This, as I said, this is the first installment of what may be a long series. It'll be interspersed with other topics as usual in the Bite of Physics series, but I want to return to this from time to time and try to put together kind of a coherent sketch of a course in introductory Newtonian mechanics, which starts the way I started actually when I was a student. Back when I was an introductory student, the usual technique was to start with static equilibrium. And things have moved now to changed a lot, so that usually the first thing that's done is simply talking about the description of motion, what's called kinematics, mathematical description of motion, which really doesn't have anything to do with physics. It's just geometry with time, describing trajectories of particles, cars, things like this, and especially talking about them in the case of constant acceleration, which is a very special case of generalized motion, and it includes a very complicated concept, in my opinion, called acceleration, a concept that trips people up all the time. So the primary idea behind this is to leave acceleration as long as possible. What we're going to do, as you see there, is we're going to talk today about static equilibrium. We'll probably talk about that for another time or two. What happens when a system has no net force or torque on it? And that's not to say no force or torque, but it is to say that the net result of the forces or torques on a system is zero. That if you have a force in one direction, and force is a vector, as we'll talk about, you have another force in another direction, or combinations of forces, such that the net effect of it is just the same as if there was no force at all. And the same kind of thing with turning forces, torques. What can you determine when you know that something is in static equilibrium? What are the equations of static equilibrium? And then we'll move in the next phase probably to talking about reference frames and Galilean relativity, to really emphasize the point that having no net force doesn't mean not moving, because not moving is kind of a weird idea. As far as we know, even to this day, there's no such thing as absolute rest. There's only being at rest relative to something else. So one can always take an object that you might think is at rest, like the chair in your living room, and view it from Mars, and you'll say, "Oh, that chair is moving," and you'll be just as right in saying that as the person in the living room who says, "No, it isn't. It's just sitting there." People can describe the motions of objects from different reference frames, and the only thing that, as we'll see from Newton's first law, when an object has no net force or torque on it, then whatever it's doing, it doesn't change what it's doing. That's the key. Then we'll talk about what happens when there is a net force or torque. And then, of course, the idea is if there is a net force or torque, things do change. So we'll talk about the concepts of what are called impulse and momentum. This is the effect of force over time, which changes the momentum of an object. And related to that, we'll talk about work and energy. That's the effect of force acting over a distance, which changes a thing called the energy of a particle. When work is done, the energy of the particle changes. And having work and having energy and momentum under our belts, we'll talk about collisions, what happens in collisions, how momentum and energy get transferred from one thing to another in collisions, interactions in general. And then finally, at the very end of the series, we will hopefully for the first time, not that I haven't already said the word acceleration, but we'll say the word acceleration more, and we'll talk about trajectories. Up to this point, we won't have talked about the trajectories of particles at all. I won't have said anything about parabolic motion of rocks when you throw them, even though I just said that. We won't talk about that. We'll talk about acceleration only at the very end. And the reason for that is because the acceleration, which is the rate of change of the rate of change of the position of a particle, is a complicated concept.